When we talk about equilibrium, we need to talk about the Chatelier's principle. Now, the Chatelier's principle in this way. If a chemical system is already at equilibrium, okay, and you disturb it, how can you disturb your equilibrium? You can disturb it by changing the temperature, changing the pressure, or somehow changing your compound concentration, either products or reactants. What will happen is that the system will actually shift its equilibrium to counteract the effect of the disturbance. So what does that mean? It's a nice general sentence, but what does that mean? So let's go through and take a look at the effect of temperature. Okay. I'm going to go temperature, then pressure, and then I'll spend the most time with concentration, because that's where we use Le Chatelier's principle the most. So if I gave you a reaction, okay, and I can put this at equilibrium, but really it almost completely, it will go to completion. Okay, so heat is released. This is an exothermic reaction, which means you could say that heat is part of my product. So if I increase the temperature that I run this reaction, it becomes increasingly harder to actually oxidize methane. Okay, so methane at room temperature oxidizes easily, but if I increase the temperature, because I'm adding heat to an exothermic reaction, it's going to prevent it from going forward. What happens if it's endothermic? Suppose I have ammonium nitrate and I'm trying to dissolve it in water. It turns out this reaction is endothermic. You can consider this as needing heat as part of my reactants. So as I increase my temperature, or increase the temperature of this reaction, because I'm increasing temperature, I'm giving my endothermic reaction more heat, and it will push this reaction forward. Okay? So in other words, if I'm in equilibrium, when I add heat, what's going to happen is I'm shifting it to the right. So when I increase my temperature for an endothermic reaction, it goes right, goes to the right. All right. So that's how we do temperature changes. If I increase my temperature for an exothermic reaction, it'll go left. So, summarize that. Okay, so let's take a look at pressure. So we can change the pressure by changing volume. So remember, they are inversely related. So if I decrease my volume, I increase my pressure. Okay? If I increase my volume, then I decrease my pressure. So let's go through and take a look at the decomposition of sulfur trioxide. Okay, so when it reaches equilibrium, here's a closed vessel. Okay, and I have my gases in here, and I'm at equilibrium. If I decrease my volume, okay, so suddenly, let me just draw it as dots, different colored dots. If I decrease my volume to, let's say the black is the sulfur trioxide, okay, 6, 1, 2, 8, and then 1, 2, 3, 4. If I decrease my volume, you can see how cramped 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. So when I decrease my volume, now all of my gases present in there, this is high pressure. So when I decrease my volume, I increase my pressure. So what we need to do is relieve the pressure. Okay? So what can my reaction do in order to relieve the pressure? So think about it. This gives me 2 moles of gas. And here I have a total of 3 moles of gas. So if I shift left, so my equilibrium is going to shift left, I'm going to make more product. Now, if you look at this, okay, 1, 2, 3, 4, 5, 6, 7, 8, and I had 8 of the green, so let me just use that for the green and 2 of the blue. So for the green, 1, 2, 3, 4, and 2 of the blue. So what I have left, okay, is I have 1, 2, 3, 4, and 1, 2. So I've decreased my particles. So if you look, with the green, I had 8 black, I had 8 green, and I had 4 blues. Now when I shift left, definitely blues in there, 1, 2, 3, 4. If I shift left, my reactants stay there, so I still have my 8 blacks. But now I used up four of these. Okay, so I created 4. Okay, but look at, I only have 2 of the blues. So I decreased, essentially, by shifting my equilibrium left when I've increased the pressure. My reaction will go in the direction to decrease the number of moles of gas present. And when it does that, it relieves the pressure. Because remember, P is directly related to N. So to decrease P, my reaction can decrease N, and that'll decrease my pressure. Okay, so that's what happens with the pressure changes. Now let's take a look at the concentration changes. So there's several ways to look at the concentration changes. So let's do, we'll just draw it, the diagram. Reactant, okay, plus reactant, okay, gives me product. All right. So this is a reactant plus this reactant gives me this product. Okay, now if I decrease my reactant, then I don't have enough reactant. So what's going to happen is when I decrease my reactant, which direction will my equilibrium shift? It's going to shift to the left because this is no longer at equilibrium. It has to shift left to decrease my product and then increase this amount of reactant. Okay? Okay, so what we had discussed was Le Chatelier's principle. Was if I have my system now in equilibrium and I disturb it, so let's say I remove some reactant, then my system is going to shift its equilibrium in order to reestablish the equilibrium point, in order to reestablish equilibrium. So in other words, if I remove reactant, then this reaction will shift left in order to try to create more reactant. Okay, I will end up though getting more of my blue reactant. And what it will try to do is get us back into equilibrium. Okay, now you say something like, well, that looks good, but this is not the same as that. Okay? I still have more blue than black. And the answer is that's true. But remember, equilibrium, we said, was at the rate forward is equal to the rate back in reverse. And we also said there's a equilibrium constant. K is my equilibrium constant. So, if this is at equilibrium, okay, I reduce my green product divided by my blue and the concentration of my red. That's not red, black. Then when I upset my equilibrium, I need to go back to this value. So by decreasing this amount, my value is too large. So I need to decrease my value. So if I increase this number and decrease this number, then my goal is to get back to K. All right? And that's the whole reason that Le Chatelier's principle occurs. Okay? We need to get back to that value of K. So, for concentration then, what are the different things that we can do? With concentration, let me just show you. With concentration, we can do this. One, if I reduce my reactant concentration, let's say this one, then it shifts left. What we just discussed graphically in the previous slide. What happens if I reduce my product concentration? I don't have enough product, so it's got to make more product to try to get back to equilibrium. So it's going to shift right. 3, what happens if I increase my reactant? It could have been hydrogen. I'm just using nitrogen for example. If I increase this, then I have too much reactant. It's going to force my reaction to go to the right. 4, if I increase my ammonia, my product, if I increase this, then I have too much product, is going to shift left. Okay? So then the question is, how can we affect the concentrations? Okay? The most common one is we add or remove. How do we add? We just go to container, add more. How do we remove it? And to remove it, there's several ways. You can remove by having a competing reaction. We can affect K through dilution. That will affect our K in many cases. And also, just physical removal. So there are just laboratory techniques that allows us to remove a product when we need to. All right? So we've talked about effects from pressure, effects on temperature, and effects on concentration. So let me go ahead and just summarize it for you. So, one, temperature. Okay, so if I have an exothermic reaction, that means heat is a product, it's releasing heat. When my temperature goes up, it shifts left. Because when I increase my temperature, I'm basically increasing the amount of product. If my temperature goes down, it shifts right. Okay. If it's an endothermic reaction, that means that it requires heat to go. Okay, so heat is basically one of its reactants. If my temperature goes up and I'm adding more reactant, it's going to shift right. My temperature goes down, it shifts left. Okay, and then let's talk about pressure. Okay, so this is with the volume change. All right, what happens is if I increase my pressure, then basically it shifts to fewer moles of gas, whether that's reactant or product. If I decrease my pressure, so this is by decreasing my volume, this is by increasing my volume, then I'll shift to form more moles of gas. Okay, so then the last one is concentration. And basically, if I increase concentration of my reactant, then it shifts right. If I decrease my reactant, it'll shift left. If I increase my product, it will shift left. And if I decrease my product, it will shift right. Okay. There's a brief mention of catalysts that will be reviewed in chapter 14 when we go through rate laws. The catalysts do not affect equilibrium. Catalysts just facilitate the reactions so they occur faster. But equilibrium is not affected. Okay, so just bear that in mind. But Le Chatelier's, in summary, those 3 points for Le Chatelier's is what you need to know. And we'll do some examples in the next slide. Okay, let's just do a quick example here. Suppose I have carbon monoxide and it's reacting with water vapor to form carbon dioxide and hydrogen gas. And the delta H for this reaction is a negative 41 kilojoules. So if I wanted to increase my hydrogen gas formation, how would I change my temperature? So you would look at this and say, this is an exothermic reaction. This is basically the heat's a product. So therefore, if I decrease my temperature, then I would move my reaction right and I would see an increase of my hydrogen there. Okay? Can I control the pressure? If I wanted to change my pressure, can I affect my production of H2 by pressure? And the answer to that, let's take a look. I have 2 moles of gas as my reactant, and I have 2 moles of gas as my product. So the bottom line is, if I increase my pressure or decrease my pressure, the equilibrium would be the same because it's 2 moles and 2 moles. So there's no way it can relieve the pressure. Okay? When I run this reaction. Okay, so temperature affects it. In this case, pressure does not. But let me ask you this. Suppose we know that carbon dioxide gas reacts with not water vapor, but liquid water. Okay? Give me carbonic acid. So, suppose here I have all my gases. I introduce liquid water. What will happen to my hydrogen gas production? Okay, so now we have a two-pronged approach. So this is the equation we're interested in. This is occurring at the same time right here at this interface. Okay? Why is this important? Because that product is the reactant here. So if I form carbonic acid, once I introduce liquid water, then I will be using the CO2, which means the CO2 concentration here goes down because I'm using it up to form carbonic acid. If that's the case, then this reaction shifts to the right. So my hydrogen gas production increases. The concentration increases because the reaction of interest shifts right. Okay, and in this case, I am affecting concentration. This is a concentration example. but it's related by having a competing reaction to affect my concentration. Okay? So that's it for equilibrium, and we'll move on from there.